A new AI system has just processed 5 trillion pieces of information in a single prompt. That is not 5 trillion words. It is physical information spread across space and time. According to Reuters, the system can handle roughly 5 million times more context than flagship models from Google and Anthropic typically consume. One way to picture that scale is to imagine reading War and Peace millions of times in one sitting. But this AI was not built to write essays, answer questions, or imitate human conversation. It was built to model reality. The company behind it is Accelerate Understanding, founded by Caltech professor Anima Annenhumer and AI infrastructure engineer Benedict Jenick. Earlier, the pair had been courted to help lead Project Prometheus, the Jeff Bezos-backed AI company that later raised $12 billion to pursue advanced manufacturing. Instead, they continued building their own system. And their bet is radically different from most of the AI industry. They believe the next major frontier of artificial intelligence may not be bigger language models. It may be AI that understands physics directly. Today's frontier systems are extraordinarily good at manipulating language. Give a model a scientific paper and it can summarize it. Give it equations and it may explain what they mean. Give it a design problem and it can suggest possible solutions. But there is an important limitation. Knowing how people describe physics is not the same thing as simulating physics. A language model can tell you that heat flows through a semiconductor. It cannot automatically calculate, at extremely high spatial resolution, exactly how that heat will spread through every part of a new chip design over time. It can explain turbulence. That does not mean it can simulate an entire turbulent fluid at engineering accuracy. It can discuss a hurricane. That is different from predicting how the atmosphere itself will evolve. Accelerated Understanding is trying to build AI for that second problem. Instead of focusing on words, its models take the state of a physical system and predict how that system evolves across 3 dimensions of space and 1 dimension of time. The company calls this physical AI in 4D. That creates a completely different computational challenge. For language, context is basically one-dimensional. A model receives a sequence of tokens. Physics is not a sequence. Imagine a cube divided into 1,000 points along its width, 1,000 along its height, and 1,000 along its depth. That already creates 1 billion spatial positions. Now track that system through 1,000 moments in time. You have 1 trillion points of context. And real engineering simulations may demand even more. This is why the 5 trillion figure matters. According to Accelerated Understanding, one inference at that scale can produce around 22 terabytes of output. One answer: 22 terabytes. A normal laptop may not even have enough storage for many such outputs, let alone enough memory to process one directly. But scale alone is not the most interesting part. The architecture is. Almost every modern chatbot traces its lineage to the transformer architecture, introduced by Google researchers in 2017. GPT, Gemini, Claude, and many other systems use some variation of that basic idea. Accelerated Understanding is taking another route. Its technology is based on neural operators, a class of AI methods Annenhumer helped pioneer. The distinction sounds mathematical, but the basic intuition is useful. A normal neural network often learns a mapping between fixed sets of numbers. A neural operator tries to learn a transformation between entire functions. That is important because many laws of physics are expressed through partial differential equations. These equations describe how things like heat, fluids, waves, electromagnetic fields, and materials evolve continuously across space and time. Traditional computers solve these equations by breaking reality into enormous grids and repeatedly calculating what happens at each point. That works. But high-fidelity simulations can be painfully slow. Caltech researchers have shown that neural operators can solve some fluid dynamics problems up to roughly 1,000 times faster than conventional numerical methods, while also working across different resolutions. The idea is not to calculate every physical process from scratch each time. The AI learns the underlying mapping from one physical state to another. This approach has already produced one major demonstration. ForecastNet, developed by researchers including Annenhumer while she was working with NVIDIA, used neural operator technology for global weather prediction. Research published through Caltech reported that ForecastNet could generate medium-range weather forecasts around 5 orders of magnitude faster than traditional numerical weather prediction while approaching state-of-the-art accuracy. 5 orders of magnitude means roughly 100,000 times faster. That does not mean AI has made traditional weather science obsolete. Operational forecasting still combines many techniques and requires rigorous validation. But it demonstrated something important. A neural model could learn complex physical evolution at global scale without reproducing every traditional numerical calculation. Accelerated understanding now wants to generalize that idea far beyond weather. The company says the same underlying AI can learn multiple areas of physics inside one model. Fluid flow, heat transfer, wave propagation, materials, and potentially many others. That is a major claim because engineering simulation is normally fragmented. A semiconductor company may use one specialized solver for thermal behavior, another for electromagnetics, another for structural stress, another for fluid flow inside a cooling system. Each tool is carefully constructed around equations and assumptions relevant to that domain. Accelerated understanding wants something more like a foundation model for physics. One model that learns patterns across many physical systems and potentially improves because those systems share structure. The company says it has observed what it calls cross-physics uplift. Training several areas of physics together can improve performance compared with models trained separately for individual tasks. If that generalizes, it could reproduce one of the most important lessons from language AI. Large language models became surprisingly capable partly because knowledge from one domain transferred into another. A model trained on programming, books, science, and ordinary conversation can sometimes combine those abilities in ways no narrow system was explicitly designed to do. The physical equivalent would be an AI that learns something from fluid dynamics that helps it reason about heat transfer, or learns structures from wave behavior that help it understand another engineering problem. But the biggest promise is not simply faster simulation. It is faster experimentation. Consider how a new chip is designed. Engineers propose a geometry. They simulate it. They examine temperature, power delivery, and material behavior. They change the design. They simulate again. Eventually, they manufacture prototypes. Then they measure what actually happens. If something goes wrong, the cycle begins again. The same basic loop exists in batteries, aircraft, turbines, materials, medical devices, and energy systems. Idea, simulation, experiment, failure, modification, repeat. This loop can take weeks, months, or years. Anand Kumar argues that AI-generated ideas alone do not solve this problem. In fact, they can make it worse. Suppose a future AI generates 1 million possible battery designs. That sounds powerful, but if scientists still have to build and test those million batteries physically, AI has not removed the bottleneck. It has created a bigger pile of experiments. Accelerated understanding wants AI to evaluate much more of that search space virtually. Its system is designed not only to predict what will happen, but also to provide directional feedback. Instead of saying, "This chip overheats," the model could potentially help answer, "Which direction should this geometry change to reduce that heat?" That turns simulation into optimization. And this is where the business implications become large. Reuters says the company sees potential applications in semiconductor design, robotics, extreme weather prediction, and geological analysis for energy companies. Take chip design. Modern AI accelerators are approaching enormous power densities. Heat is becoming one of the most important constraints on performance. Engineers must optimize the chip itself, packaging, cooling, materials, and data center systems together. An AI that accurately models those interactions faster could shorten design cycles. Now consider robotics. A robot world model normally learns from visible scenes, objects moving, hands interacting, bodies navigating environments. But reality contains important variables that cameras cannot directly see. Force, pressure, temperature, stress, fluid dynamics, friction. A physics-native model could potentially give robots a richer internal understanding of what will happen when they interact with objects. Then there is energy. Companies searching for oil, gas, geothermal resources, or minerals must interpret huge geological datasets. The underlying processes occur across three-dimensional structures that evolved over enormous periods of time. Again, the problem is fundamentally physical, but there is a reason to be cautious. Accelerated Understanding is a newly launched company, and many of its most impressive numbers currently come from the company itself. A system handling 5 trillion context points is technically remarkable, but context size alone does not prove that its predictions are accurate enough to replace trusted engineering simulation. The same lesson applies to language models. A model with a larger context window is not automatically more intelligent. For physics, the bar may be even higher. A chatbot can hallucinate a sentence and still be useful. A simulation used to design a billion-dollar semiconductor fab cannot casually hallucinate how heat moves through silicon. Engineering requires verification. Small numerical errors can produce very expensive physical mistakes, so the real test will not be whether this AI can generate beautiful simulations. It will be whether companies can compare those predictions against experiments and existing high-fidelity solvers and consistently trust the results. There is another challenge. Physics has rules. An AI model trained on data might learn correlations that work inside its training distribution, but fail under genuinely new conditions. Researchers have been working on physics-informed neural operators partly to address this problem, combining training data with mathematical constraints derived from physical equations. That may be essential if these systems are going to move from impressive demonstrations into engineering infrastructure. And yet the direction is significant even if the current system is not the final answer. For most of the current AI boom, intelligence has been defined through language. Can the model answer harder questions? Can it write better codes? Can it reason longer? Can it use tools? Accelerated understanding is asking a different question. Can AI understand how nature evolves? That may require architectures that look very different from ChatGPT. Annan-Kumar and Jenik say their models have already been trained at sizes up to 1 trillion parameters, with scaling experiments reaching 35 trillion. More importantly, they claim context lengths beyond 5 trillion at inference. This is not simply another company trying to make a chatbot with a slightly higher benchmark score. It is an attempt to expand what a foundation model can represent. Not a document, not an image, not a video, but a physical system unfolding through space and time. And there is an interesting twist behind the company itself. Reuters reports that Annan-Kumar and Jenik were offered an extraordinary opportunity connected to Jeff Bezos. A proposed Project Prometheus offer would have given them a combined 35% stake, with Annan-Kumar positioned as the public face and scientific leader. Their combined annual salary was proposed at $1 million initially, doubling to $2 million after 3 months. The proposal referenced more than $2 billion in committed funding rounds. They walked away. Prometheus later raised a $12 billion Series B and is pursuing AI for advanced manufacturing. Accelerated understanding instead continued independently. That creates an unusual experiment inside the AI industry itself. Two groups are attacking a related problem: how to make AI useful in the physical world. One has enormous capital. The other is betting heavily on a particular scientific architecture. We do not yet know which approach will matter more, but the larger trend is becoming clear. Language was the first great environment conquered by generative AI, because humanity had already digitized an enormous portion of it. Physics is harder. Reality cannot be reduced to a paragraph. A jet engine contains flows, heat, vibrations, and materials interacting at the same time. A storm covers millions of square kilometers. A semiconductor contains billions of structures packed into a tiny physical space. To understand those systems, AI may need to process information at scales that make even giant language model context windows look small. That is what makes the 5 trillion number interesting. Not because bigger numbers automatically mean better AI, but because it shows how different the next generation of artificial intelligence may need to become. ChatGPT learned to predict what comes next in language. Accelerated understanding is trying to predict what comes next in reality. And if AI can eventually do that accurately enough, the biggest consequence may not be a better chatbot. It may be that scientists stop waiting months for the physical world to answer every question.